We will continue from where we left off last time. This is all still part of introduction. I'll probably cover most of it today. Maybe a bit will be left for the next lecture. And then we will move on to specific topics after that. We talked about the Industrial Revolution and how important it was. And within a matter of about 150, 200 years, there was such a dramatic transformation that took place. What we must remember is that it was driven by need. It is not that out of people's fancy they just did something. Okay, it was not that. It was genuinely driven by need. Probably the greatest need that was created at that time was the need for clothing. Clothing means people, of course, did wear clothes, but the clothes were not very attractive to look at. They were not. The color was off-white, dull brown, or yellow, and so people then said, and it was all cotton, and people said, hey, we must try and make nice white clothes. Like if you have a bed sheet, you want it to be nice and white. You don't want it to be dirty looking. So there was a demand for this kind of white clothes, and that then actually led to this whole concept of bleaching. In fact, what was done, you can see there was a way of treating clothes with alkali, and then it was dipped in buttermilk and then exposed to light. And then they just left it outside, and they found that the clothes do whiten up, and there's a very good, reasonably good bleaching effect. But they also realized there were several issues. One was, of course, in England and mostly in many places in Europe, where the sun is not so bright, that it all is very dependent on the weather conditions. And then you require so much of milk, where you'll get so much of buttermilk from. So these were limitations, and always the best of technologies have been built based on appreciation of limitations and then trying to overcome those limitations. Now, then after that, around 1758, it was very interesting. There, somebody had the smart idea of dipping these fabric in dilute sulfuric acid. Maybe weakened the clothes a bit, but probably not too much, and they got a beautiful whiteness, and they could get rid of this buttermilk business. So that was again a huge advance, and you can see that it created a demand for sulfuric acid. Okay. Later on, there was another important breakthrough by the French scientist Berthollet, and where for the first time he was able to show that you can just expose a fabric to chlorine gas and it became white. And so that was they call it an unsuspected bleaching effect. They didn't know what chlorine will do at that point. Okay. But then people also realized that chlorine, how are you going to transport it anywhere? It's a gaseous stuff. Okay. And then someone had the smart idea that by that time you could get potash from burning of wood. They just passed chlorine into potash, and it became a nice solid. Today we know it as potassium hypochlorite. And later on, again, someone had the brilliant idea of replacing this potash from wood with lime, which was, so they knew how to fire limestone and make lime. So they passed the chlorine into lime, and it formed calcium hypochlorite, and that greatly reduced the cost of producing bleaching powder. It was a revolutionary work that was done. I hope you can see how interesting it was. The interesting thing again was that it, of course, spurred demand for chlorine. It spurred demand for acid. It spurred demand for alkali because you needed both. And then someone would have thought, hey, sodium chloride is what? It's got the constituents of sodium hydroxide and HCl, just a salt of those. And the idea must have occurred to them that why don't we try and make chlorine and sodium hydroxide, etc., from sodium chloride. They had no idea how to do things. That's another very interesting thing. You're listening to things which were ahead of the actual invention. But conception is very important. Conceive ideas, and then only it's worth working on it. But most of us, because we are working on things which are already well known, so that part is conveniently given the miss. You just take it for granted it exists. But that's not the way it was. Okay? Someone had to conceive, and then someone had to develop technologies to make these things happen. And later on, as you will see, the first technology that was made to produce soda ash, which was the alkali, was not the Solvay process. There was another process, and funny enough, that process of making soda ash, which is an alkaline substance, required sulfuric acid, and so it created a huge demand for sulfuric acid. So this is the way in which technologies evolved and the demand for products actually evolved. And obviously, when you are talking about the entire population, it has to be bulk production. So that's how the concept of producing these things in large quantities came to the fore. Now, another very interesting thing, and you can see how smart they were, whenever they got into some difficulty, they found a way around it. Like chlorine was a gas, you can't use it. Then Tennant had this idea of purging chlorine through lime, making hypochlorite, and it's a beautiful solid. It doesn't have the strong oxidizing power of chlorine, but it has got sufficient oxidizing power. And in fact, in a way, it's better. It moderated the oxidizing power of chlorine, and so it did less damage to your clothes. And so you could bleach your linen with calcium hypochlorite, and that was easy to transport. People could go to a shop and buy that solid, okay, bleaching powder. Okay? Whereas you couldn't do that with chlorine. So I hope you can also see that the creation of products was also based on the convenience of use, not just use, but convenience of use. This is another very interesting example, and I thought I'll link it up. When people manufactured acetylene from calcium carbide, and acetylene, of course, became very important for especially for welding applications, and also to make many chemicals, although that came a bit later. But again, acetylene had the same problem as chlorine, that it was gaseous. And there wasn't such a development in material science and compressors that time that you could make these things in cylinders like you do today. So they had to find a way around it. You can see 1896, there was a beautiful intelligent work where they just took acetylene and they found that it solubilizes, it dissolves in acetone. And so you could get vast amounts of acetylene just in a soluble form. Then you just cut the liquid, and wherever you require the acetylene, you warm up the solution, and the acetylene is liberated. Okay, so it didn't actually participate in a reaction; it was just solubilized in the acetone. They again solved a huge problem, and this is something that the smartest people do. That they are able to see something which already exists, an idea of making a gas into a solid, hypochlorite. And I just say, can I learn from that idea or do something very similar in my circumstance, wherever I have this kind of a problem? So all the time at the back of your mind, keep this, that where did I hear something like this? Can I make use of it in whatever I'm doing? And I showed you before another commonality, like Bohler thought he had made ammonium cyanate, but actually ammonium cyanate was unstable and it decomposed and then reformed into urea. And then I showed you how similar kind of a double decomposition, a decomposition reaction can take place, a redox process between ammonium and NO2 minus, and you can liberate nitrogen, and which is used in the explosives industry. Many times it's not as if you have to do everything from scratch. You might always find some source of inspiration and look for that inspiration. Now let's come to another. It is probably the most important because especially if you don't have fertilizer, there will be no food of at least this amount of food. To feed the population would be next to impossible without fertilizers. It is not as if people many hundreds of years back had no idea that there are certain things that promote the productivity of crops. That's not true. There was. In fact, the people who were probably most advanced in that area was the Inca Empire in Peru. What they had, Peru, it was very interesting. There was a mountain of bird droppings, and that is known as the guano deposits in Peru. Very, very well known guano deposits. And these people, the Inca Empire, they had actually taken this deposit, spread it in their fields, and found that they get very good growth of their plants and the productivity of crops from the same acreage of land. This is where this thing that I can keep something at a phenomenological level. You say, oh, guano deposit, great, it does this, fantastic, good, okay. But then, somebody else would have said, can I learn something from this deposit? And the German scientist Humboldt traveled to Peru, and he collected some of this guano deposit and brought it back. Europe was quite advanced in the area of analytical science already, whereas Peru, they were they just used to do things. Okay? They didn't have that kind of knowledge. Humboldt came back and did an analysis and found out that it is quite rich in nitrogen and phosphorus. And that was a very nice piece of work. And then subsequently they said, oh, there is also a source of nitrogen in chili saltpeter, and which is even larger. Okay, so why don't we try out some chili saltpeter? They tried it out, and they found that that also leads to good growth of plants. And so the correlation of with nitrogen, okay, was established. Later on, they also found that if you just take the ash from the wood, then the bones from carcasses, and it is spread on the fields, that again, over long term, that the fertility of the land improves and they got higher productivity. All in all, that is what led to the establishment of today. What we all, you ask anyone, hey, what are the three essential fertilizers? Everybody will tell you NPK. But it was this work that really created that knowledge. And that was done by another German, not by Humboldt. Humboldt probably came and analyzed it and found that there is nitrogen and phosphorus. But it was Liebig who was the one who was able to do the systematic studies which were actually led to this correlation. They knew that woods of plants have potassium. They knew that they figured out that animal bones have got phosphorus, and they also knew of that chili saltpeter has got nitrogen. So, they would have done also very systematic studies where they may not have put all the fertilizers at one go, put one at a time, and seen the response of different crops. And so what did they do? They advanced this entire knowledge of agriculture, soil science, everything through this. Now, Liebig was not only did he correlate all these things, Liebig was so brilliant, that he said, I find that these bones take a long time to act. The plants don't respond to these bones and all fast enough. And he just treated that with sulfuric acid. Why would he have treated? One was, of course, everybody knew that sulfuric acid is a strong acid and it may do something. And also remember there was only a very limited repertoire of chemicals. It's not as if I had thousands of chemicals to play with. I had those kinds of things. I had alkali, I had acid, and a few of these other things. And whatever you have to do, you have to do with that. Yeah. That was one. And the other trick that you could play is you can heat up things. Those are the really two things that you could do, nothing else. So, he treated it. Basically, what happened was that the bones, were transformed into a more readily assimilated form of the fertilizer. Later on, of course, a source of calcium phosphate was identified because bones are predominantly calcium phosphate. Another very interesting thing which was found uh, basically by the French was that when they were doing all their studies on coal liquefaction, making coal gas, that in the gas they found that there is quite a bit of ammonia. When I say quite a bit, it might have been about 2 to 3% by weight of the coal, but still substantial because you burnt so much of coal. Again, coming from this concept of it's not usable. I can't use ammonia in the feed. I need to convert it into something more easy to transport and handle. Liebig had this brilliant idea that basically ammonia is an alkaline substance. Why not treat it with sulfuric acid, and made ammonium sulfate? That was the first commercial fertilizer, commercial ammonium nitrogenous fertilizer, ammonium sulfate. The rest of it was natural, the sodium nitrate from chili saltpeter. So long before the Haber process, people had made synthetic fertilizer, ammonium sulfate. Okay, and I hope you can see the progression and how smart these guys were. Then, of course, there are two kinds of scientists. One is the people who actually come up with the primary knowledge. The second are people who are very good at identifying maybe alternative resources, making things cheaper. That is their strength. And so they were able to continuously keep improving. Like from the potassium got from wood, they were able to find that there was a huge deposit of potassium in a not exactly as potassium chloride or something, but still very rich in potassium, which was there in Strasbourg. So that became then the source of potassium. Okay, and so this was the advent of fertilizers, and one after the other, inventions took place in the fixation of nitrogen, which we will discuss later on, how it gave birth to the Haber process. But even before the Haber process, there was another process which was there. Likewise, when we are talking about the alkali, we will see how the quest to convert from a batch process into a continuous process is really what gave birth to the Solvay process. All right, let's also look at another of these very important drivers, which was colors, dyes. As I told you, people had solved the problem of whiteness of fabric, but now they got more demanding. Said, hey, we want colored stuff. We want colored fabric. We don't want to only wear white clothes. And of course, it was mostly the royalty who could afford it. Look at, they first were able to identify important blue colors. One of them was, of course, our indigo, which was a vegetable dye. And then you had from the cabbage type of substances, they were able to identify a blue color. So there were two sources of blue, from these vegetable sources. Then they found a series of red colors. There was something that they found from insects, different kinds of colors, vermilion red, some other type of red, carmine red. So all of this was done. Then came Brazil wood, because insects were difficult to handle. But then they found, there was a wood, Brazil wood, which gave a beautiful red color, and that's how the name Brazil got created. Brazil is based on Brazil wood. I hope you can see how things advanced. And then came another very, very important dye, which was subsequently made synthetically, which was alizarin. It was derived from a herb. This is alizarin. Okay? And we know that the chemistry and the business of natural colors is not new. All you have to do is go to Ajanta caves. All the paintings there are made from natural colors. There are these painters in, it's a very traditional family in West Bengal. All they do is make paintings in natural colors, Beautiful. This is all based with natural colors. Okay? So wonderful. But people at the same time realize, okay, that there are limitations. As I told you, I mean, you can only make that much of dye from insects. Even from Brazil wood, okay, there's only a limited amount that you can make. Although things like indigo, etc., there was a substantial production which you could do, and if subsequently jeans, etc., became popular, the blue jeans, it was all because of indigo, nothing else. Okay, now then you'll see the transformation, and this is another concept which became popular, which is that I take something which is a natural material, but then I improve on it. I do something to it. This was a wonderful example, the Murexide. This stuff, this is the structure, which of course was worked out much later. The structure was not known at that time, but this much they knew, that Murexide had a fair amount of nitrogen in that molecule. That they knew. And someone would have correlated and said, hey, guano deposits have so much nitrogen. And they were able to isolate uric acid from guano deposit. And then what somebody did was that they treated that uric acid with nitric acid, and they were able to make a compound, a color, which was for the first time, they were able to make a beautiful purple Murexide. This was not all. Someone realized that these colors are great, but when I put it on fabric, they're not held on so well. And they created the concept of a mordant, which is something which complexes with the dye and then attaches to the fabric quite nicely. So the whole concept of a mordant was created and Murexide was made. And then, so you move from natural materials to a semi-synthetic material, because you started with a natural material and then basically transformed it. Subsequently, people started looking at all synthetic materials. The first such dye was picric acid, which was, you'll probably know from your laboratory work. It gives you a very bright yellow color, doesn't hold on so well, and it's just trinitrophenol, picric acid. That was created, but not a very successful dye, because it was not fast, and people also realized that it caused a lot of skin irritation. The real breakthrough, and today, what I think all of us would call as the first true synthetic dye, was made by Perkin, and it was known as Mobine. This is again very, very interesting. This is Mobine, by the way. You can look at all these things that happened in an isolated manner. So and so made Mobine, this made this. It's not that. What was the spirit of the Industrial Revolution? All these colors which were associated with the aristocrats, things like the mauve color, purple color, they were all part of royalty. And suddenly the common man said, hey, I can also afford these. I can have the same color as the kings and queens they wear. Okay. And so it was really in the spirit of the Industrial Revolution. Okay? Because that was at the heart of the Industrial Revolution, to make things affordable, to make the masses enjoy what only a few handful of people used to do before then. And all of this basically made that possible. Okay? So you must look at how important these things were from that perspective. Those three, the dyes, the fertilizer, and the fabric, they were really the, I will say, the core, the big things, okay, which were done. But around that time, the chemistry of and the frontiers of metallurgy were being developed, and especially aluminium. Aluminium was a, people realized that aluminium is a great metal. It's very lightweight, it doesn't tarnish. People knew this would be a great material to make, for example, utensils and things like that. Aluminium actually was a very costly material, again, which is something that only the rich people could afford. The invention of a new process which made aluminium so cheap that it became one of the cheapest metals, right, really was the symbol of the frontiers of metallurgy. How did it happen? This is another thing that you must understand, and especially as chemical engineers, for you it is vitally important. You see, we talk about temperature, we talk about pressure. Now, what temperature are you talking about? What temperature were these people in 1600 talking about? They were only talking about the temperatures that you can achieve by burning wood or burning coal, and that's it. It's a few hundred degrees. So your limit of temperature was that. Pressure. Pressure was as good as atmospheric ambient pressure. There was very little of anything that was known which was high pressure. It just didn't exist. Okay, because you required special reactors to hold pressure. Where are you going to get those things from? There was, metallurgy was also in its infancy. Such materials have still not been created. A real breakthrough was the electric furnace, which was invented by Henry Moissan, the same person who also isolated fluorine, and the same person who also made calcium carbide, and from which we got acetylene. How was he able to make calcium carbide? Simply because he had invented the electric furnace. So once the electric furnace was invented, and people realized that we can go to 3000 degree temperature, maybe even higher. They said, oh, we can melt all the metals, all these ores and all. I mean, I can recover the metal from it. It melts. It is not just about chemicals. It is about the facilitators, which facilitated the production of chemicals and materials. And that happened because of advances in high pressure and high temperature. You'll see, I mean, the birth of polyethylene was entirely dependent on high pressure, and so was ammonia synthesis. So that's how important it was. So you as engineers must realize how important it was, the role of the engineer in really facilitating all of this chemistry. Other very important things which happened, as I told you, just like you saw in the case of Urexide, cellophane, which later on gave birth to the movie industry. All of it was from regenerated cellulose, natural material, and which was processed, so semi-synthetic. So this concept of semi-synthetic came to the fore. People at that time realized the importance of photography. You could not only rely on your memory to remember people. People said, if I could have a photograph of my loved ones after he or she is gone, how wonderful. And that gave birth to photography, the need for being able to remember people who are no more. And later on, it was not just about remembering people who are no more. People realized that for some funny reason, people actually enjoy the memory of an event more than the event. When they're seeing the event, they actually don't enjoy it that much. They enjoy it much more when they're later on thinking about what they did. And that's what we all do. Why are you so desperate to see something in your friend's face in a mobile? It's because You're seeing a live person, but the photo looks more interesting than the live person. It's funny, but that's how we are. So all of this led to a massive demand for photography. And also another reason was that you could not go to every place. But moment I could take a photograph, I could share it with the world. And so these were the drivers, these are the things that made photography so important and brought it to the fore. And that gave birth to all the chemicals that you required to take a photograph, to fix the image. All of that to create a film, photoresponsive film. So all of that was vitally important and part of the Industrial Revolution. Okay? And then, of course, the birth of plastics. Of course, the birth of plastics had already been created with cellophane. But that was not the only trigger for plastics. We will discuss some of the other triggers. Later on, people realized that why only make beautiful clothes? Maybe I can make my building also beautiful. Why should it be so drab and brownish color and whatever? And the concept of paints was created. And people then had started having beautiful houses, which I could paint. People started even painting their nails. And so people started finding all kinds of interesting applications of paint. People wanted to look, they wanted to smell good. That created perfumes and fragrances. People realized that wood is not just about burning and getting potash. I can extract many chemicals from wood. I can get medicines from wood. And so that gave birth to chemicals and wood. And also I can treat wood to make it more durable, that it will last for centuries and won't rot. So again, a very, very important area. The quest for fertilizers I have already discussed, which we'll cover more, and how it led to what is today probably considered, if you ask 8 out of 10 people, if not 10 out of 10, that what is the greatest chemical process that has ever been created, I think probably you will get the answer, Haber process. And that is the magic that it created, the Haber process. Then the same thing, the electric furnace, which opened up the metallurgy sector, that same thing, which also gave me acetylene, that also through a magical twist of calcium carbide, I could actually make cyanide. And the moment one could make cyanide, people realized that it's a wonderful chemical to purify gold from gold ores. And so gold was created, and there was a mad frenzy for gold. And gradually gold came center stage. Gold then became the glittering jewel. Gold later on became the most important material on which bartering took place. All kinds of things took place because of gold. Okay? Now, when they had made acetylene and they could reach high temperatures, but again, someone had the smart idea that if I take pure oxygen, now if I burn acetylene, I can get a much higher temperature. And everybody didn't have an electric furnace. And so I could take calcium carbide, or by that time I can take it, I can generate acetylene. And if I could make a pure oxygen, then that would open up new avenues for high temperature processes. Where can I get pure oxygen from? Why not air? The concept of liquefaction of air was born out of that. But again, let me tell you, the people who liquefied air were actually not doing it initially to liquefy air. I mean, to make oxygen. They were actually trying to make a cold medium, basically as a replacement for things like dry ice. And in the process, of course, it was integrated with rectification. Once the Joule-Thomson effect had taken place and and I could liquefy air, and then someone developed the process of how to separate out nitrogen and oxygen. So there were two components. One was that I liquefied my air, and the second was I rectified it. So that's what these two famous people, Linde and Hampson, did. We always seem to know Linde, but actually Hampson, Britisher, did it slightly ahead of Linde. People also knew about fermentation. That was known because as long as people were consuming fermented liquor, you got sugars and things, and you could ferment and make alcohol. That was known. Okay? And so once it was worked out by Pasteur, the kinds of enzymes, bugs, which actually cause these transformations, that these are natural processes based on enzymes, that again gave birth to biochemistry. And the entire concept going from fermentation, ferments, okay, to isolated enzymes. And opening up the whole process. There are so many drugs today which are based on enzymatic processes. And the entire area of asymmetric synthesis, making chiral things, because the birth of stereochemistry had also happened. People realized from the days of Pasteur, and people realized that there are certain optical isomers which are more active than the other isomer. And so these two were a perfect marriage, that I could take enzymes and make very stereoselectively products. Okay. So that again became a huge area. And as I told you, people also started realizing, just like the electric furnace, I need facilitators. Okay. And one facilitator was the electric furnace. Another was the material. The moment metallurgy had come to the fore, I could make stainless steel, etc. I could make reactors, I could hold pressure. And then people said, fine, I can do temperature, I can do pressure. But do I understand what is the effect of these things on conversion? And the whole concept of chemical equilibria and the interplay with temperature and pressure came to the fore. And people also realized that kinetics and thermodynamics don't always go, most of the time. They found that they go hand in hand, but not always. That there are many cases where the reaction kinetics is not understood. There are some things which progress in the nanosecond time scale, and there are some things which you can expose for hours and nothing happens. So the whole area of reaction kinetics, and again, that in turn also gave birth to catalysis, because people realized that the best way to alter the kinetics is through what subsequently became known as catalyst, although at that time people didn't know about it. Okay, what is catalysis? Is it all clear?
Yes, sir.
Okay.
Yes, sir.
All right. A lot of the work in the early stages was based on bulk inorganics, like we talked about sulfuric acid, chlorine, soda ash, and those were big stuff. The organics was still pretty much dependent on natural materials, because that was the source of carbon. And what? Cotton. Cotton was, people realized it's cellulosic, so things were made from cotton. People could also do things with other parts of a plant, from roots. They could make fibers. Okay? People found out that the banana leaf, if I shred it, I can get fine fibers, and they're very strong, excellent tensile strength. And so people knew how to make natural fibers. Wonderful. Even cotton, I can open it out, I can make fibers out of it. So those kinds of things existed, but limited impact, right? The beginnings of petrochemicals, and it synchronized with also the production of automobiles. People wanted fuels, to run those things. Once oil, which burnt much more readily than coal, okay, which had a higher calorific value. Once you got addicted to oil, people realized, oh, these petrochemicals, I can also convert into chemicals, not just use as a source of energy. Of course, in terms of the fuel, one of the greatest inventions at that time was the discovery of tetraethyl lead, okay, which I had to just put in ppm quantities into my fuel, and it prevented knocking. And it was, the discovery of tetraethyl lead which really gave birth also to things like the concept of additives. Additives are things which are required in tiny amounts, but they have such a profound effect. And so that everything doesn't have to operate in bulk quantities. There are many things which I can just take tiny amounts, put it into something, and it does something magical. So, the chemistry of additives became important. High pressure, just like we talked about high temperature, high pressure became important. Moment I then had high temperature, high pressure, I had the birth of petrochemicals and of course acetylene. People at the same time, Schrodinger, he had unraveled the molecular basis of many of these materials like cellulose, etc., and recognized that these are polymers. And then the quest for making synthetic polymers began, and it was the person Schrodinger who really taught us, the chemistry of giant molecules. He called them as giant molecules. People knew about rubber, but they again saw the limitation of natural rubber in terms of its availability. And because automobiles were fast spreading and rubber had many other applications, including surgical gloves, so there was a need to develop synthetic rubber. That became a huge thing. New plastics got created. Very, very interesting what led to this breakthrough in plastics was something very different. Can anyone tell me why was synthetic plastic propelled? I mean, what could have been something that they conceived as an interesting possibility for plastics? Well, I'll give you a hint. It's not as if glass did not exist. Glass was already there. I could make containers out of glass. What is it that they perceived as limitations of glass or attractiveness of glass?
It would break easily.
Exactly.
Plastic is durable.
Brittleness. And they thought, because by that time, they already knew that some of these plastics don't break. They're quite flexible. I mean, that was, of course, a negative attribute of glass. What was the positive attribute of glass? What was nice about it?
Sir, it could withstand high temperatures.
Yeah, that's one. Not very high temperatures, but it could withstand reasonably high temperatures.
It can be molded into different shapes and sizes.
That also is very important.
It does not react easily with.
Wait. This is great. In fact, you're giving many ideas which are new. Okay. So first was it is brittle, withstands high temperature, not too reactive. Is that one of you said?
Yes, sir. I said not too reactive.
What else?
So it can be molded into different shapes and sizes.
Wonderful. Can be molded into different shapes. Anything else?
Transparency.
Wonderful. Wonderful. Okay. Glass. Okay. And you can see I've written the search for transparency. It was actually more important than even those other things, apart from brittle. Brittle and transparency were the two things. Brittle was the negative attribute, transparency was the positive attribute. So people wanted to make transparent plastics, and they kept on trying out various things to make transparent plastic. And in the process, they could not make it transparent, but they invented a variety of polymers. And finally, of course, they made something almost as transparent as glass, which we know today as perspex. And that was the invention of ICI, Imperial Chemical Industries, the same people who also invented polyethylene. I hope you can see it's very fascinating. And the moment, people had been able to crack oil and make ethylene and make small molecules like acrylic acid, okay, people then found that the sky is the limit in terms of making polymers. They made styrene. Okay. Now they said all of these are the building blocks, and Schrodinger has already taught us about polymers. And so there was a massive thrust on polymers. And because petrochemicals was like oil was like water, it suddenly became available in plenty. And then, of course, you had nylon, which was invented. Again, all of these are related to polymers. And the same Henry Moissan who invented the electric arc furnace is the person who also, for the first time, was able to isolate fluorine, elemental fluorine. You know how reactive it is, elemental fluorine. And he is the person who was able to isolate it. Once fluorine had got created, and people realized that it's got magical properties. Subsequently, of course, the whole area of Teflon, etc., came up, but people realized that fluorine has magical effect on many pharmaceuticals. That was again a big thing. It just happens that I'm in the international committee for selecting the next Henry Moissan Prize winner, and it's done by France. So there is a prize which is given once in, I think, 4 years or 3 years, and is given for someone who has done outstanding work in the area of fluorine. Okay, I mean, and so that's his greatness, that even today people remember him as someone who did something brilliant, and also made the country famous. It made France famous. When we talked about petrochemicals and this whole business of trying to make small molecules out of it basically involved cracking. So I had to crack a big molecule and make a small molecule. And that gave rise to the area of catalysis, which was related to petrochemicals. So there was catalysis which was known for inorganic chemicals like ammonia, like sulfuric acid, contact process. We know all that. These were very, very famous catalysts. But the catalysis of organic oils, polymers, etc. came to the fore. And these are the people who did it. And if you ask me, this probably more than anything else propelled chemical engineers to the forefront. Chemical engineers, after that, there was no looking back, because they became increasingly important once this whole area of petrochemicals had opened up. Soap substitutes. All the soap was made with animal fat, but people said, yeah, but again, limited amount. I have to find other ways of making a synthetic detergent. So soap substitutes was a very big thing. People started falling ill, and it was like a contagion. And it was not just people. You could wipe out entire crops in one day if the infection spread to the fields, where you've got thousands of acres of land under cultivation, and suddenly it's all wiped out. And so the whole area of the onslaught on infectious diseases, how do I prevent it? How do I protect my crops? Were major drivers of the entire process of what we know as chemical technology. And then you had, of course, France's coal-based chemicals. People realized that Why only petrochemicals means oil? With coal, I can do a lot, and many countries have coal, but they don't have oil. And also, coal, as I told you, gave ammonia, and it was, in fact, the first synthetic ammonium fertilizer. And so these were all very, very important. People also realized that there are many chemicals like the tetraethyl lead, which are actually used by the end consumer, like a surfactant. It is there in so many formulated products. I need to emulsify. Okay, I have emulsions. People realized it's not about only benzene, methanol, that there are chemicals which give you a unique effect. And that effect is mostly applied at the consumer's end. And that was the development of specialty chemicals. That's how it happened. In the previous slide, what you saw is the birth of petrochemicals. It was just beginning to take off. And then it gradually became a carbon-based world. Probably, I will say, maybe about 70% or 80% of chemists and chemical engineers are engaged in a carbon-based world. All of the technologies, all of the industries, etc., everything is based on carbon. And it happened because of the rise of petrochemicals. It started booming. Let me ask you, we talked about the birth of petrochemicals. I mean, it was all based on crude oil. How long do you think crude oil has existed? I'm saying, like, when they were able to drill and get oil, then of course all of these industries started booming. I just thought I'll ask you that how long has that kind of thing been around?
Sir, century and a half at max.
You're actually not too far from the answer. We'll have a look. It's important that we know this, and there's a specific reason why I'm asking you this question. The rise of petrochemicals, as I told you, means that it was a carbon-based world. Name anything. Ziegler-Natta, polymers. You just have to see how much polymer is being produced in the world every year. It's based on the work of Ziegler and Natta, who were able to come up with a very efficient process of polymerizing ethylene and propylene. You had elastomers, so a new rubber then became an unbelievable product. You know, the quality of rubber. I mean, today, nowadays, you see the rubber tires and all that we have. I mean, it lasts for years. That's how good it is. The entire area of polyurethane and the area of insulation, all our refrigerators, everything. If you did not have proper insulation, you would not be able to use them. Okay? And people were able to make unbelievable foams out of polyurethane with excellent insulating properties. Polyurethane, of course, has many other applications as a resin, many other stuff. PU is all over the place. Fibers, chemical, so all the clothes that we wear today, it's all synthetic, it's all polyester. And so it all came really because of the rise of petrochemicals, agrochemicals, medical breakthroughs. All the primary feedstock were all this kind of carbonaceous materials. The only exception was the penicillin breakthrough, which of course was one of the landmark events, the bioprocess of making penicillin, which was done by Pfizer company. But pretty much everything else was all due to the rise of petrochemicals. We need to also understand what is meant by bulk chemical, fine chemical, and specialty chemicals. Can anyone tell me what might be bulk chemicals, what are fine chemicals, and what are specialty chemicals? Bulk chemicals are also known as commodity chemicals or basic chemicals.
So bulk chemicals are those chemicals which are used to prepare fine and specialty chemicals.
Wonderful. Wonderful. So, in fact, they are the precursors. So, for example, things like benzene, toluene, xylene, ethylene, methanol, these are all bulk chemicals. And out of that, you use such chemicals, and likewise, there would be inorganic bulk chemicals, sulfuric acid, caustic soda, chlorine, fluorine, and without those, you cannot make the fine chemicals, and the fine chemicals are typically lower volume products compared to the bulk chemicals, because a bulk chemical can have hundreds of applications. And each of these fine chemicals would be produced in smaller amounts. And the bulk chemicals today are all produced in continuous processes. Whereas fine chemicals, still, a lot of the fine chemicals are batch processes. The volumes are less, and also they are very, very complex to make. Sometimes, it can involve 10 steps to make a fine chemical. And fine chemicals can sometimes be intermediates, which are then used to make the final chemicals, the final products. In many cases, we know them as specialty chemicals. Those are the ones that the consumer finally sees, or the consumer is actually using in their products. You don't really use ethylene or ammonia or any such thing. Those are all bulk chemicals from which these things are derived. So just make a note of it. All of these things were vitally important. The thing that happened relatively more recently is the alliance of chemicals and electronics. Today, the world it's a carbon world, okay, and the other is it's an electronic world. Name all your goods. I mean, whatever we are doing now, it's all because of electronics or ability to communicate, the way we are doing today. All your computers, your mobile, everything, it's all electronics world. But what you must not forget is that do not treat the electronics as just some transistors and chips and all. They are based on primary chemical feedstock. Like, for example, you need extremely pure silicon, 99.999% purity, and then you selectively dope those to get the kinds of transistors, etc. we use today, microprocessors. And so at the heart of it are some chemicals. And so the processing of those chemicals, that how to make things exceptionally pure, that was a new technology, new direction, which was given to the chemical industry, that how to make things with less than ppb levels of impurity. So a huge area in itself, the polishing up of chemicals. Let me show you. One is that you can look at it and gloat, and beginnings of petrochemical, rise of petrochemicals. Hey, how about the fall of petrochemicals? Believe me, that's going to happen by the time you all are 70 years old. Petrochemicals would have fallen by then. You will have to look forward. We cannot bask in the past glory. Things are going to change. Let me show you how precarious the situation is. Look at this. Like one of you said, about 150 years, not bad. 1825, so close to about 200 years back. The first commercial natural gas production took place. Not even 200 years ago. The first oil well, oil was dug out from Azerbaijan, Baku, 1846. And once that happened, then you had, of course, the four-stroke engine, and that started pulling in demand. There was demand. People then also were able to find a way of being able to distill kerosene from crude oil. And the aviation industry was ultimately born from such products. The first refining of oil, actually setting up a complex, was done by Rockefeller in 1863. And also look at the pace of progress. We are talking about oil 1846, and we are talking about 1863. Less than 20 years. And in that time, we already had an oil refining hub. And then you had Edison, with the light bulb and the need for power, the combustion engine, the Wright brothers. You can see the Ford company was founded in US, and all of this started pulling in massive amounts of oil. But people then realized this oil is not going to last, and the major discovery that took place, and you can see, is just about 80 years ago. 80 years ago. Today, 70% of all oil, crude oil, comes from the Middle East. And oil discovery was 1938. Not that long. Oil then became a very volatile material. Oil prices like 79 to 81, it went from $13 to $34, almost a factor of 3. Then it collapsed, and giant companies were born. Companies like Exxon, Mobil. These were the biggest companies in the US. I mean, today it's Facebook. Today it is Microsoft. But these were not the companies. They were not even born then. The companies which were really big companies, they used to hire, recruit thousands and thousands of engineers. Okay? But these companies, and then they started aggregating, they merged, Exxon and Mobil. Nobody would have imagined number 1 and number 2 becoming Exxon Mobil as one company. So there were massive changes that were taking place, but we are talking about all things that happened because of a discovery that is not even 80 years old. And at the same time, what also happened was that there were major accidents. One of the biggest accidents was in 2011, and that actually ignited, a debate on the safety issues. Because safety, this is only safety related to petrochemicals, but safety issues had come to the fore. Till that time, it's all production, this, that, everything, demand, supply. But that they also have a sinister side. If you're not careful, that became clear. Let's just look at now what the situation is. If you look at this last year's data, I just dug this out. Last year was, of course, a year because of the pandemic that oil consumption had reduced. It was about 91 million barrels. That is equivalent to 30 billion barrels a year. One barrel is about 159 liters. So it gives you an idea of how many million tons of oil we are talking about, which are required every year. Okay, and where are we? This is OPEC today. You can see their figures. This is in millions of barrels of oil, and this is India. Absolute peanuts. One of the lowest, and not just India, China. Very little oil. The oil is pretty much here, and it's in countries like Venezuela, in Canada. These are the countries which have large reserves. We have nothing, and that's the reason why we are importing almost all our crude oil. ONGC produces only a limited amount, very, very negligible quantity. Don't get fooled by all this indigenous production. I mean, bulk of it is imported. And look at this, that India and China, look at our population. Look at the total population of the world. We're talking about something like 7.5 billion people. Between us, we are talking about roughly 3 billion people. And you can see just 0.5% of the world's oil resources with 20% of the world's population. That's the seriousness of the problem. We are, of course, in a bad shape, very poor shape, but let me tell you, the entire world has a problem. And I'm not even talking about environmental issues yet. I'm just talking about availability issues. US Energy Information Administration, if you look at many of these statistics, what basically is becoming very clear is that We have oil probably till 2040, liquid fuels, but 2050 onwards, the situation is looking extremely dicey. The point is that we have seen what happened to the climate, how much of CO2 got pumped into the atmosphere. It's happened because within 80 years, we have virtually wiped out what nature produced for us over millions of years. That's not sustainable. This is another statistics from British Petroleum, and they have categorically said, how long will world's oil reserves last? 53 years is their estimate. In other words, you all will be around 70 years old when you will find there's no oil. And I'm not talking about there's no oil in India. Or India, so oil will be over long before that. India, in any case, is going to import. So what's going to happen is that there's going to be such a fight for the resource. Today, if you see a lot of countries talking about climate change, the need to switch over from fossil fuels, okay? Although, people are talking about it from an environment point of view, don't get fooled. They have all realized that it's all going to end in any case. That is not just a CO2 issue. There isn't going to be oil. It's not that anyone is doing anyone a great favor. And what has happened now, the issue, the big threat to a country like India is that India has some coal. That coal reserves might last us maybe a few hundred years. May not be that much also, because we are already importing coal. But why are we importing coal? Because our coal is not so clean. So, and you know that there are strictures which have been put, like China has said that no plant which they are going to construct, power plant anywhere outside of China, will not be based on coal. India has 70% of its power requirement comes from coal. And if they're going to stop use of coal because of pollution, because of excessive CO2 production, then we are going to be in for deep trouble unless there is an alternative source of energy. Can anyone tell me, coal especially has been singled out. Why coal? Like if I take natural gas and coal, which is a better fuel?
Natural gas.
Natural gas.
And why is that?
Energy
right.
released per mole is more.
Yes. And what else?
Less emissions of carbon dioxide and other harmful gases.
Excellent. Because although the calorific value of natural gas is higher, and if you take coal is just carbon. So when I burn it, I get CO2. Whereas when I'm burning natural gas, I get basically CO2 plus H2O. Both of those are giving me energy. The burning of that H4, in the methane, when it is getting converted into water, there's also enormous release of energy. So that's really what is giving me a much higher calorific value together. Okay? And plus, natural gas does not have the contaminants that coal has. You can see what havoc is being created now. Europe has run out of fuel because they went excessively for natural gas and somebody has cut off the supply and they're struggling now. So, and we are talking about 2020. Every 5 years, the problem will get worse and worse and worse. So if you have to look at the future of the world, you need to ask yourself, what do I have to do in the future? There's no point talking about all this. It's not going to help you. In 1958, the Shell company had created what is known as the Hubbard curve. This curve is fantastic. It's not got wrong. What they had shown in 1958 was basically that we will peak around 2000, and then basically our reserves are going to decline, and you can see at what level they are going to reach by 2050. So there's going to be a mad scramble. Right? And if you try to take out more, you'll pay a bigger price. You might be able to discover future sites. Even that has been factored in, future discoveries. But the situation is terribly bleak. Bear that in mind. So what you have to see is that when you're looking at industrial engineering chemistry, and if energy is one of the primary things that drives our processes, what happens to those? And one thing is that maybe there will be alternate sources of energy, okay, power. That has to happen. Otherwise, civilization will come to an end. But the chemicals that we have got so used to, which are all carbon based, what are we going to do about that? Are we going to have new kinds of materials? Or a much wiser thing to do would be to conserve this only for production of petrochemicals and find some other ways of meeting the energy requirement. So that kind of strategic analysis and thinking is also something that all of you will need to look at, because you all will be in senior positions. The world will be in your hands. You will have to decide what you want to do for your future and for the future of your children and grandchildren. You are going to be alive then. I won't, but you will. You will see. You can write it down today, put it in the locker, and open it 50 years later and see what happened. Now, we saw with the petrochemicals, and we will see with the things like sulfuric acid, ammonia, etc. We are really talking about large-scale production, the bulk production, bulk chemicals. Now, I just wanted to ask you, what is your perception about the merits and demerits of large-scale production? Let's try to write it down and rattle it off. Tell me quickly. It can be advantages, disadvantages. We'll segregate it later on. Just tell me what you think.
There will be much depletion of natural resources.
Rapid depletion of natural resources. Huh? That's what you're trying to say, right?
Yes, sir.
Okay. What else?
So since they are produced in a bulk, they are available as cheaper raw material.
Wonderful. Bulk production drives down cost. Yeah. What else?
Sir, you're trying to cater to the masses, increase population, so production on large scale caters to the masses.
Ideal for catering to the masses. What else?
The environmental impact.
Greater environmental impact. Or we can say not greater, more concentrated environmental impact, right? Because it's over a small area. What else?
Safety issues.
Wonderful.
Sir, boost economy.
Waste management.
Yeah, let's put the more concentrated environmental impact. We can put waste management issues there itself, huh? Rather than as a separate point. Okay. What else?
Sir, we can export.
Export. Can promote export. I'm not very sure. Yeah, you export, but that's true.
Sir, small scale industries are in danger then.
Ah, wonderful. Threat to small scale industries. But then, we also saw that bulk chemicals are the ones from which you make fine chemicals. Small scale industries actually ought to be focusing more on the fine chemicals. You understand? And that way you can reduce the fear of threat. Is that clear?
Okay, sir.
If they are competing in the same space. Okay, so I've qualified it. All right?
Not flexible.
Not for everyone, because as I said, I mean, if they are small scale industries are making something very specialized, there's no really competition with these large scale production guys. Because large scale, it may not be amenable to producing those extremely sophisticated chemicals. So it can happen. I mean, I'm not saying that even those cannot be produced on large scale, but by and large, there's a segmentation in terms of the types of chemicals.
A lot of people can be employed.
Well, a lot of people can be employed when you have large scale production. Many times, the guys go for large scale production because they're trying to cut down on manpower. Because every small scale unit would again require people, so actually you can employ more people on a smaller scale production than on a large scale.
Sir, the threat of overproduction.
Threat of overproduction. Okay. Anything else?
Not flexible means we cannot change the circumstances of
Okay.
industry.
Less flexibility.
High risk of accidents.
So safety issues. Higher risk. Higher risk means we can say greater consequence of accident. Because it will be such a massive accident, obviously many more people can get killed, right?
Yes.
So the consequences will be more severe. We'll put more severe consequences of accidents. Although, let me tell you, many small plants, actually, they have a worse accident record. You see the number of accidents in and around Bombay in small plants, right? They're very high. Large plants actually have relatively less accidents. But if you have an accident, it can be a dangerous thing. Now look at yourselves. Think about yourselves and then look at this question. Large plants require greater sophistication. And perfection. That is what you can do with your training. You see, your training is training you to do things perfectly, or should, by the time you are finished with your degree. And so you will find that people and they can offer higher quality jobs. It makes a demand on everybody, the reactor manufacturer, the logistics manager. There are all kinds of issues that come up in large scale manufacture, and some of it will be advantageous because your training would allow you to work in such places. Whereas in many small places, they may not have that level of sophistication. They may not actually have a requirement of a person with your brilliance. They might say, for me, a diploma guy is enough. And so it creates an opportunity for more sophisticated knowledge. Agree or disagree?
Yes.
Agree? Do you agree or do you disagree?
Yes, sir. Agreed, sir.
Okay. I think you've given an excellent list. Now, I will really focus on one issue, which is safety and its consequences. What, for example, happened in nuclear power plants? It's otherwise a fantastic technology, nuclear energy. It's a low carbon technology. There's no carbon formation. You generate high amounts of very concentrated power. But every time you think about a 3 Mile Island or a Chernobyl or a Fukushima, and you think, oh, if this happens, then we are gone. And so it has put a fear in people. And these large plants can also have very, very serious consequences. And you'll have to create much larger buffer zones so that the population is not getting exposed. Let us see some of the major accidents which have really propelled the concern for safety, more than any other thing. And what it also showed is that the greatest of companies can have accidents. This is what happened in BASF. Okay, they had a storage facility for ammonium nitrate fertilizer, 4,500 tons, and that exploded. And look at the thing, that explosion was such that the pressure waves from that explosion ripped off roofs 18 miles away. 500 to 600 people died. Many were injured. Many people lost their homes. 80% of the buildings in that area were destroyed. One accident, all it takes is 1 minute and it's gone. That is the severity, right, of and the biggest threat of large plants. What happened in India? We have had the worst disaster ever, the Bhopal gas tragedy. Can someone tell me what happened?
So MIC gas was
MIC gas was released. Great. And how did it happen?
So because of cutting corners in the plant, the safety of the plant was compromised, and
No, how was it compromised?
because of water, sir.
Water.
Yes, sir.
Fantastic. Where did you hear about it?
So net geo.
yes, sir,
Net
net
geo.
geo.
I'm really impressed. For those who may not be knowing the details, and you might also know it a bit superficially. So let me just go through in brief what happened in Bhopal. Right. So firstly, 1984. So we are talking about 37 years ago. Tragically, in a country where we had the worst disaster, there was very little taught on safety. After that, I mean, I would have thought that it would have become absolutely the first thing that you teach to people. But we didn't. We were engrossed in all our routine ways of teaching. And so it didn't look like we learned a lot from the accident. Right? It's just amazing. But what they were trying to produce, over there was this pesticide known as carbamide. They were producing it. They had to introduce this carbamide group. That's the pesticide. So they reacted alpha naphthol with methyl isocyanate. Okay, and that introduced the carbamide over here. So this H ends up as part of the nitrogen. So it's just an addition that takes place. The chemistry is clear?
Yes, sir.
Okay. Now, MIC is produced from N-methyl carbamoyl chloride, this molecule. In the process, there is a release of HCl. That is then MIC. That's how you get it. This stuff is produced from the reaction of phosgene and methylamine. It will basically just kick off HCl, the H from here and the Cl from here, and this part is getting added to this carbonate. Phosgene, in turn, because phosgene is a dangerous chemical in itself, you cannot actually transport phosgene. It would be too risky. So phosgene, the commercial way to produce it is from carbon monoxide and chlorine. You can get COCl2. And you know that carbon monoxide is extremely dangerous for human health. Why? Because it competes with oxygen for the hemoglobin. So if you have got CO you'd surely die, because all the hemoglobin would get bound irreversibly to carbon monoxide, deoxyhemoglobin. And carbon monoxide, of course, where would you get it from? How would you get CO?
Bosch process, water gas.
Yeah, that would be one process to get it from the water gas process, good. Or you might be able to do a controlled combustion of carbon and end up with CO. Not a total combustion, but a controlled combustion. That's what it is. Now, it released MIC, but there could have been multiple disasters. If, for example, phosgene, etc., which is highly toxic, if it had got released. So just bear that in mind. Now, how exactly did the MIC get released? And mind you, you can see that the total injuries people have suffered is today more than 500,000 people. Not only were there deaths soon after this accident, mind you, it was gas inhalation, it wasn't a fire. But effects of that poison have been such that long after, many women who became pregnant, they gave birth to children who were deformed, and so there was an after effect of this, which was equally devastating. Not just the immediate deaths that took place. How many of you have seen this label? Has anyone seen this label?
On some tank, I think.
On some tank. Brilliant. Very good. This is known as an NFPA label. In fact, in many of the chemical bottles also you'll see this label. The NFPA stands basically for the National Fire Protection Association, who created this label. Okay. It has 4 quadrants: red, yellow, blue, and black. Red basically stands for fire, yellow for instability, blue for health, and black for specific hazards and what precautions you might have to take. The severity of these is denoted by these numbers 0, 1, 2, 3, 4. So the lower the number, the less severe it is. Higher the number, more severe it is. Black is basically if you are trying to alert on some specific properties, which you need to be careful about. Like if it's a very strong acid, you might just write acid. Or if it's a very strong alkali, you might write alkali. If it's a strong oxidizing agent, you might write this. Why? Because if I'm storing it, like if I'm storing an acid next to an alkali, and if something breaks and spills, it will be such an exothermic reaction. Or if I'm storing an oxidizing chemical next to a fuel, you can imagine what can happen. If there's a spark and if something is leaked out. We think water is safe. Wait till you react it with sodium. I mean, water is deadly. All right. So you might have to say, use no water. You might put a W and cross it out that do not expose it to water. If you look at the NFPA label for methyl isocyanate, I think you will have a very clear understanding of how dangerous the stuff is. Firstly, it has a very low boiling point, so it's extremely volatile. The NFPA label clearly says W, cross it out. It's terrible for your health, MIC. It's very unstable. And look at these numbers. Maximum is 4, don't forget. And it's also flammable. So whichever way you look at it, it's a horrible chemical. What happened on that day, I will not read it out, but you can read it. And this is from an article in the New York Times, which was published, you can see in 1985, January. So it was soon after the accident. I did not see any such article or anything from any Indian person, not even a scientist. And so, that's the tragedy. Another thing I realized that, we were not equipped to really even comment on accidents. We did not have that competence. So what they did was they interviewed a lot of people in the plant over there, and it seemed like it was because of a water leak. What it basically says is that the leak began, according to several employees, about 2 hours after a worker whose training did not meet the plant's original standards was ordered by a novice supervisor to wash out a pipe that had not been properly sealed. That procedure is prohibited by plant rules. Workers think the most likely source of the contamination that started the reaction leading to the accident was water from the process. Look, something as benign as water, somebody will say, "Arey, pani se saaf kar lo." That guy probably didn't know about NFPA label, didn't have much of an understanding of chemistry. The other things that were found, one was, you see, because MIC is so volatile, it is meant to be kept in refrigerated tanks, all right? But the refrigeration unit was not working. So it aggravated the problem. The refrigerator was not working. Second, if you are a person who is careful about safety, you will always ask questions like, "Agar ye hua to, tab kya hoga?" I've seen there are two kinds of people. One kind will say, "Kyun hoga? Hum sab theek kar rahe hain. Nothing will happen." And the other is saying, "Arey baap re baap, if it happens, do you have any kind of remedial measure?" Another remedial measure that they had was that they are supposed to have a spare tank of MIC. So for every filled tank of MIC, they're supposed to have a spare tank, because if there is any problem that develops in the MIC tank, then they can quickly transfer the MIC into the spare tank. But what they did was that the spare tank was also full of methyl isocyanate. Probably, the Carbadil was selling very well. Okay, a lot of money to be made. And somebody said, "Arey, spare tank hai na? Spare tank pe aur methyl isocyanate store kar lo. Kya problem hai?" So they would have used it up. And when the situation came, when they needed a spare tank, there wasn't any spare tank. So one after the other, the alarm systems were not working properly. But even if the alarm systems had worked, I don't think they would have been able to do too much. The reason is because, you see, it is a gas. The gas, once it leaks out, it spreads all over the city. Gas is not going to be confined within your factory. Gas will go wherever it can go. What these people were also taught for estimating leaks, whether MIC is leaking, that MIC leakage you can figure out if your eyes start watering. Whereas you ideally you should be using an MIC sensor to sense the MIC. So obviously it's a multinational company, Union Carbide. They were not following the same stringent practices that they were following in their plant in the US. They had a plant in West Virginia where probably the safety procedures, protocol were much more stringent. And it was not being followed here. Now let us look at the chemistry of what happened with water. MIC can react with water in an exothermic reaction. And it's very exothermic, the reaction. The products of the reaction are as such, if anything, much less harmful than MIC. It forms dimethyl-urea. It forms trimethyl biuret and carbon dioxide. Nothing is unsafe. Now, and CO2, all of these are harmless stuff. There's nothing harmful. So what was harmful? Harmful, harmless. What was harmful?
The reactant itself.
Sir, the heat which is evolved.
Yes, and what happens because of that? William.
Sir, explosion.
Wonderful. Okay, one was heat. Anything else? And anything else? 5 seconds. You all are a smart class, so you should be able to answer. CO2. CO2 is a gas. So, you know, the reactor, it would build up pressure. It built up pressure, and then what else can the safety valve can't protect you? It would have given way. And when the CO2 is escaping, firstly the temperature is high, and the MIC, not only from the vapor phase, but you know, when things are gushing out, okay, huge amounts of gas, there will be also a lot of entrainment of liquids. It will carry the liquid with it. So vapors of MIC plus the liquid of MIC as an entrainment would have gone. Is it clear? Has everyone
Yes, sir.
understood?
Yes, sir.
So heat which was evolved and the pressure build up due to carbon dioxide release led to the reactor giving way and releasing the contents. If it had been a refrigerated tank, firstly the reaction with the water might have been less, the rate of reaction, and the entrained stuff may not have happened. That's what I think. The vapor pressure would have been much lower. Look at the tragedy of what happened. On Monday, we will continue and finish the portion on inherent safety. How do you make a plant inherently safe? How do you make your processes inherently safe? So we will touch upon that and cover a few more topics, and we will be through with the introduction, and then we will go on to the individual topics.